what we did limits and differentiation in higher dimension. I hope you got some idea of it. We still have, we can set up some tutorial and have a discussion over it. There's one more thing remaining in differentiation, and that is obviously when you learn one-dimensional differentiation, you also learn about some of the applications of differentiation. Okay, application within mathematics. In other words, you learn how to optimize things. Actually, so you learn optimization through the derivative, one-dimensional derivative. Okay, we also going to do optimization. Okay, so I want to do integrals. I want to cover this chapter first, and then we can do that bit of optimization as well. Or maybe if there would be a need, then we're going to do some part of optimization as well. There are also some exercises about optimization, some small exercises in exercise. You must attempt those. And so what we are going to do today, we're going to start doing integration actually. Okay? Start with the integration. So how we will start? Our main objective is to, is to do the integration or the various versions of integration over some kind of surfaces. Okay. In general, we want to define things from Rn to Rm, or Rn to Rm. Okay, but in particular, if you want to visualize them, we are very much interested in that, how to integrate the maps from say R2 to R and R3 to R2 to R3 and this kind of a maps actually. So if you have been given a graph of a map, then how to integrate over it. Okay. Now you through all of our discussions, you might also have realized that so integrating, doing integration over surfaces is our bigger goal actually. Okay. And you will see lots of application during our physics discussion actually. Physics is all about applying this multivariable calculus to the, this stuff that we're going to cover about the physics. So we saw that surfaces, can be understood as, one way to understand surfaces is that you have a continuous stream of curve and you bunch them together and you get a surface as a result actually. Okay. So we saw, for example, if you combine lots of parabolas, so you get roughly a half cylinder shape. So if I want to, for example, so the trick is this. So if you want to define integration, for example, on a cylinder or half of a cylinder or over any surface actually, which is made up of the curves, the first thing would be how to define the integral over the curve actually. So what would be the meaning of defining integral over the curve? Then we can extend it to the surfaces. Okay. So the objectives for these chapters are very interesting. And why I'm telling you, because you should know that where we are heading actually. So the things that we are doing, there is a purpose behind it. Okay. So how will we start? We'll start our discussion with paths and the curves. Okay, in Rn in particular, we'll be very much interested in 2 and 3 dimensions practically to look at the things. And the next thing that we're gonna do is that you will see that integration here is not like the integration that you have learned in, for example, one dimension actually. Okay, so when you want to integrate something on curves, you also have to ask a question. Okay, you are integrating what? Integrating what? So what we're going to do, so we define, for example, paths and curves in Rn. We're going to study a lot of properties of paths and curves. Okay, properties of paths and curves. So that would be another, topic of our interest. In other words, if you have been given a path in a space, okay, how to say that this path is a good path, okay, or how to say that this path is a differentiable path, for example, and this path is a smooth path, or how to say that, okay, for a path you can also ask a naturally question that what is the length of this path actually, what is the length of this path? Okay, and once we will study we will also talk about it that okay, if you have paths, you can connect two paths and you can create a new path actually. Okay, so you can have multiple paths, you put them together, concatenate them and create new paths. So well, in the beginning we will, maybe today we're going to talk more about the curves and paths actually. Okay, in Rn and some of the properties of it actually. Then what we're going to do, so what was the scalar field actually? So imagine I defined a curve C actually, and C is basically is going to be some subset in Rn, okay, in particular in R2 and R3, because if I draw a curve in three-dimensional space, each of the point of the curve is also a point in R3. So I can see curve in R3 as a subset of R3 as well. Okay. Now if it is a subset of R3, we know on R3 we can define scalar fields and vector fields actually. So what's in a scalar field? So a scalar field is a map that takes a point from R3 and assigns it a scalar actually. And what's a vector field? It's a function that takes the points from R3 and assigns them a vector actually. Okay. Now if I have this curve, okay, and since a scalar field is a kind of a thing that takes the inputs from R3, okay, and assign them in a scalar, now these inputs can also be chosen from the curve actually, because these are also points in R3. So in other words, when I am saying that I will input these points into, for example, in a scalar field, and I will have some scalars, the meaning of that would be that to each point of this curve I will assign a scalar actually. Okay. So this scalar could have what meaning? So you can imagine, you are a one-dimensional object and you are living on this curve actually. So you are kind of a bug living on this curve. Okay. Then each point of this curve, physically could mean that, ideal situation actually, because there's nothing one-dimensional, truly. Okay. But that's how you start actually. You start with the ideal thing and then come to the realistic thing. So I have a curve. So on this curve, what we're going to do, we will define a scalar field. Okay. And what is the meaning of defining a scalar field on a curve is that take the points of the curve and substitute it into the scalar field. So that is going to mean that to each point on the curve we are assigning a scalar. Okay. So now what is interpretation that a scalar can have? For example, that scalar can represent temperature. Okay. So I can say to each point of this curve, which is physically representing something, I am assigning a temperature. So in other words, I am interested in the temperature throughout the curve. Okay. You can talk about, for example, density of something. So imagine that this curve is basically a rod. Okay. So kind of roughly a metallic rod or wire something, and it's a charged wire. Okay. And every point has some assigned quantity of charge to it actually. So every point of the curve is charged. So what that would mean actually? So that would mean that you have a scalar field on the curve. Okay. But so that would be the meaning of defining a scalar field over a curve. Okay. And then since we can, for example, assign to each point in the curve on the curve, for example, a scalar, then why can't we assign a vector actually? So if we assign, for example, a vector field over a curve, that would mean that to each point onto the curve you are assigning a vector. So what does physically that would mean? That imagine you have some one-dimensional object and something is flowing over it actually. Okay, so something is flowing over this, what do we call curve. So what does it mean? So it means that every point, okay, of that liquid or whatever thing that is flowing over it is going to have a certain direction over curve. Okay, so So we'll define curve, their properties, then scalar field and vector fields, and then the key thing would come that, okay, if you have a scalar field actually, like the temperature, like the heat, like the density, how to integrate it? And what would be the meaning of it? So imagine you are interested in total density of something, over this entire curve actually. The question is how to compute that total density. Okay, or how to compute the, the total heat associated with that curve. Or, that would be the meaning of integrating a scalar field but on a curve. Okay? And the next question you can also ask is that, okay, you have a vector field, okay, something is flowing over it, and you are interested in the total flux, that how much of the total quantity is flowing over it. So what would be the meaning of it mathematically, that, okay, you have a curve and a vector field defined over it, and now you want to integrate that vector field over that curve. Okay? So that would be another objective that we like to do. So we like to integrate, okay? We're going to like integrate, how to integrate scalar and vector fields. Scalar and vector fields. Can you see where we are heading? So this is important. You should have a clear objective in our head. That's what we are doing. Otherwise, things would be abstract. You will be saying that, what's going on? But you will know that where we are heading. Okay, so on curves. Okay, and finally, so what was the most fundamental theorem that you learned, for example, in your theory of integration? The fundamental theorem of calculus. So you can ask, are you going to have a fundamental theorem of line integrals here? The answer is yes. You can approve it. Okay. So we take this. So what we're going to do afterwards, okay, since we know, think about it. So that's objective in this chapter. So can you see where we are heading? So I know how to compute the area, not area, but length of the curve, how to define a scalar field over it, vector field over it, how to integrate it, take a some vector field, and what is the fundamental theorem of for the line integrals. And I know what is surface. So surface is something when you bunch up the curve. Now you have machinery already, so you already have a theory of vector fields and scalar fields over curves. So now you're going to take them to the surface, because every surface is made up of basically essentially curves. So you can really extend it. So you will see this would be the chapter where we have to put the hard work, okay, the real effort. We have to understand everything. You see the defined integration, and then the questions that you are asking about the curve, now in the next chapters you're going to ask about the surfaces. So imagine to every point on a surface, okay, some scalar is associated. So imagine charge is distributed all over the surface. Okay, so what I'm interested in, how to compute the cumulative charge over the entire surface actually. Okay? Or something is flowing over the surface. So how to compute the total flow of it, or flux of it, or velocity, and lots of questions actually. Okay. So what we are doing is that we are developing, or we intend to develop a new machinery that will allow us to do the calculus beyond, what do you call, our classical traditional calculus. Okay? And we'll do with the purpose. And you will see that all of this stuff will be, very useful when we are doing the electromagnetism. Okay? So let's move ahead. बातें नहीं काम करते हैं. This is good that we should start. So we will start with the paths and curves, and then we will talk about some of the properties, how to compute their lengths, and how to compute the area under the curves, and different kinds of things. ठीक है जी? One of the interesting problems that we're going to, for example, deal with today. Luckily, I have my own headphone. Okay. So what we have learned so far, that if you have a curve in 2 dimensions, you know how to compute the area under curve. But imagine now your curve is not living in 2 dimensions, but it's living in 3 dimensions actually, and looks like something like that. Okay, something like that, or maybe you can assume it to be any curve actually. The question is how to compute the area under such wiggly curve actually. Isn't it? That would be a very interesting question actually. That you have a wiggly curve which is sitting in this space. Okay, it's not like a curve embedded in the 2 dimension. So the question is how to compute area under it actually. Okay. And you will see our techniques are going to be very natural. Okay? Techniques are going to be very natural. So if you want to compute this area, so imagine there is a curtain is hanged with this curve actually, and try to find the area of the curtain. Amazing stuff. Okay? So get excited and be excited for it. I'm very excited. So a lot of new things, have fun, and to make sure that you are learning this stuff, solve exercises. You also have to do the boring part as well. Once you learn it, it becomes a next part as well. So let's just start with them. So I hope you also heard about the parametric curves.
Yes.
In your calculus 2 course. Okay. I'm not going to get into the all details and length and breadth of the parametric curves, but essentially what we say, these parametric curves are the kind of curve. We're going to name them as path here actually. And we slightly defined them in previous chapter as well. Okay? Because we wanted to define that how the Fresher derivative sends the tangent vectors from one path to another path. Okay, so in order to define that, we defined some path. So what was the path actually? So we say that imagine you have an interval in R, okay, and you are doing what? To each point over this interval, you are assigning a point in this space actually. Okay? To each point, you are assigning a point in this space. And then you are combining all these points and you get a curve out of it. Okay? Then this curve is a parametric curve where these inputs are, roughly, or the input variable is playing the role of the parameter actually. Okay? So why you call it a parameter curve? Because all these points x, y, z. So if I take a point, arbitrary point x, y, and z. So this is not just x, y, z, but I know that this x and y and z are depending on an input from this interval. Okay, so this is what that you learned in your courses actually. So what we're going to do, we're going to generalize it into higher dimensions. So what's a path? So let's start defining the path. So suppose I have a P, a map from I into Rn, okay, from I into Rn is a continuous map, okay, and you always have to think continuous in what sense, and I'm going to keep on reminding you, continuous map, okay, then this map P is called a path actually. So it's a path. Okay. So this continuity is not continuity in one dimension but continuity in Rn. And we know that a function in Rn is continuous if each component is continuous actually. Okay, so it again breaks down to the continuity that you learned in your one-dimensional calculus actually. Okay, because each part of the path, because if I say that P is a path, then it takes an input T from the interval I should write where I is an interval. Okay. Then how does it going to look like abstractly? So the P of T is going to be, so it's going to have, so T is an input from I, but P of T is an output in Rn, so it's going to have n components actually. Okay. So if greater than n components, so it means that there would be n functions, okay, which would be playing the role of the component, okay, where each of these functions is what? Pi is a map from I to R actually, okay, and when I'm saying that this is continuous, so each of the Pi is continuous actually, okay, so it's a continuous map. So take an interval, so for example in R3, take an interval, okay, and meet, that's your interval I, and map every single point of this interval into this space x, y, z. So it's an abstract point x, y, z, but x, y, and z depends on, what do you say, on the parameter t. Okay. So if I'm in 3 dimension, R2 dimension, I'm not going to use P1t and P2t and P3t. I'm going to use this more natural notation of x of t and y of t and z of t actually. Now here the x of t is not just a number, but it's a function in time actually. So it's a map from I to R actually. So each of the component is a function. Okay. All right. The next definition, if in addition you have a path, okay? So I have a path P from I to R, B, Rn, be a path. So I have a path. Okay, I'll do some examples of it if you have to worry about it. Okay. That is differentiable. Okay. That is differentiable. What is the meaning of differentiability of a path? That you have a map and you are also assuming that it's differentiable, in other words, its Fresher derivative exists. Okay. And we know for the path the Fresher derivative is easy, just simply differentiate with respect to time to each component. So this is important, that we shouldn't forget what we learned, because we learned things so that we could apply here. Okay? So don't take every single word that you are writing as, so if I'm going to say differentiable, since you have learned calculus 1, you're always going to think from that differentiability point of view actually. Well, you have to, at least, push yourself to think about the differentiability according to the space actually. So if you are in R, yes, your differentiability is same as the differentiability in R actually. But if you are in Rn, you know that what the meaning of differentiability is. So you should have a clear picture actually. So that is differentiable. And if, in addition, I have a point in the interval I, where if you evaluate the derivative of the path, okay, what would be the derivative of the path? So path is like, you can treat roughly in your sketch, you can say that okay, you have a particle that is moving in space actually, okay, but there is also involvement of time as well, because it's moving in space. Okay, so if it is moving in space, so the path is going to represent what do you call displacement actually. Okay, and the derivative of the displacement is okay. So imagine you have a path that is differentiable, and if this derivative at a point t naught and I is non-zero, okay, in other words, it's a point where the particle is not stopping actually. It has a non-zero velocity. Okay, it just keeps on displacing actually. Then I'm gonna say that P is regular. It's regular at a point t naught. Okay. So what do you mean by the regularity of a curve at a point t naught? That you should be able to compute its velocity at that point. In other words, its derivative with respect to t evaluated at t naught should be non-zero. Okay. So that's a local property. So if you have a one point where it is, for example, the velocity or the derivative of the path is non-zero, you're going to say it's regular at that point. Open. In other words, for this definition, we are going to assume that I is an open set actually. Okay, for defining path, you don't need assumption I could be anything. Closed interval, open interval, finite interval, semi-finite interval, could be anything. Okay, but since you need differentiability here, so the most natural assumption is that you need the openness of the interval I actually. Okay. Okay. So if P is regular at any point in I where I is open, then P is regular. Okay, P is regular. So the path is regular. Okay. Can you interpret the regularity again? So it's a kind of a motion. I mean, if you assume it physically, it's a kind of a motion which doesn't stops throughout the interval actually. So it has a non-zero velocity onto the all points of the interval. So that's what we're going to call it a regularity. Okay? The physicist would call it having a non-zero velocity at all points. Okay?
Sir, path will represent trajectory or velocity? Or displacement? What path will represent?
The path is going to be, the path is going to be a trajectory.
Trajectory.
Okay, it's going to be a trajectory.
With respect to time.
Yes. Okay. But for a fixed t, it's a vector. It's a vector in Rn, or it's a point in Rn. Actually, it's a point in Rn. Or it's a way to say it. Okay. So here's a quick example, a very interesting example, which says that imagine you have a map from R to R2. Okay, and the curve looks like this actually. So P of t is t cube t square actually. Okay, so if this map is a path, okay, maybe yes, is this map in the path?
Path over.
Why it's a path?
Continuous.
Because both components are continuous. Yeah. Okay. But when you're going to plot this path, you're going to get basically a cusp actually. And the cusp is going to look like something like that. Okay. So it's going to look like something like that. Okay. So what do you think? Which point is going to be the controversial point where you can't kind of compute the regularity?
Origin.
Origin would be, because it has a kink over it actually. So let's see that how does the origin behave actually. So what would be P prime of t? Okay. So it's going to be P prime of t is going to be 3t square and 2t. Okay, and so the domain is entire R.